Now we're going to go to a problem that you guys have a worksheet for. On the top left-hand corner it says Test of Significance Introduction to Practice. Although it doesn't go through all the steps that you need for the AP exam, it's a great way to see why significance levels actually do matter, and then see how our test would actually compare to that significance level. So the problem is the mean score of all students who take the AP Stats exam last year was 2.8 with a standard deviation of 1.3. Assume that scores in the population were normally distributed. So that's a good thing to know. I'm going to highlight standard deviation 1.3. Assume that scores were normally distributed. This year, Miss Bliss of Bayside High thinks her 57 students will do better than the population of all takers of the exam. So she gives them a practice exam how they do. So a few things here. We know that the population mean is 2.8. Population standard deviation is 1.3. All right, it's normally distributed, so that's kind of probably find a z-score somehow. And then our sample size is 57. All right, so what is the hypothesis Miss Bliss would like to test? So we're going to go ahead and say our null hypothesis is pretty much what our population is talking about. So population mean is 2.8. Our alternative hypothesis is pretty much she thinks her students will do better. So alternative would be greater than 2.8. Okay, this is a one-tailed test because we're only looking to see what's the probability that it'll be greater than 2.8. It would be a two-tailed test if it was mu does not equal 2.8. Okay, I'm just going to go ahead and state mu is mean AP stat score. All right. Part B. What is the sample distribution for the mean score x bar of a sample of 57 students if the null hypothesis is true? So this is going back to what we did maybe like 2 chapters ago. Okay, so we have to see the sampling distribution, not the population distribution. These two numbers would be the population. So our sampling distribution, so we know the mean would also be the population mean, so that's 2.8. However, the deviation of the sampling distribution is a little bit different. Okay, remember these are all in your formula book. So we have to take this 1.3 and divide it by the square root of 57. Let me go ahead and plug that into the calculator. All right, I'm going to round to 2 decimal places, 0.17. All right, we're going to go ahead and make a sketch of this distribution. Here's my number line. The center is going to be my mean. We have 1, 2, 3, 1, 2, 3. So 2.8. And I'm going to add 0.17 to each tick mark on the right. All right, and then subtract on the left. Alright, so there's my distribution, so part B. Suppose that a sample data gives x bar of 2.9. So in that specific sample, we have 2.9. Your sketch. So go ahead and bring out pink. Sorry, my purple pen. 2.9 is going to be right around here. So the sample data gives x bar of 1.5. All right. Explain which result your students is actually greater than 2.8. So notice we're looking at which one's more extreme. If the true mean was 2.8, that means by chance of this 3.15 happening is really low. So I would say it's 3.15. Good evidence. I'll fix this up. That the mean score is greater than 2.8, since the chance that happening is very small. Alright, so it's the chance of that happening, meaning getting 3.15 as the mean. Alright, so on to the back. So now we're going to those terms that we learned last time. P-value. Remember, P-value is the probability that measures the strength of evidence against the null hypothesis. Our alternative hypothesis is greater than 2.8. So what we want to go ahead and figure out is the probability that X bar is actually going to score greater than, we have to do it for both values, so 2.9 and also 3.15. Greater than or equal to 2.9. Okay, so what we have to do is figure out what the z-score is. I'm going to go ahead and do this off to the side over here. Z is equal to 2.9 minus 2.8 over standard deviation of 0.17. And this is all sampling distribution. So we'll do that here. Alright, my z-score is, let's see, 0.59. Alright, and then put that here. Alright, greater than just really means 1 minus probability that your z is less than 0.59. If you look on your z-score table, or table A, in your textbook, it's 0.7224, and that equals let's see, 0.2776. Okay, is for scores that are greater than 2.9. So the probability of actually getting a score greater than 2.9, it's about 1 out of 4 chance. That's a pretty high chance. Okay, so let's look at what if we have greater than 3.15. Let's go ahead and find the z-score for that. Oops, 5. Alright, right around 2.06. Same process as last time. This is 1 minus, if we look up 2.06 on our z-score table, 0.9803. Alright, and that equals 0.0197. Okay, so remember p-values are probability, so this is the p-value for x bar being equal to 2.9. And this would be the p-value for x bar equaling 3.5. Which of these are statistically significant at the significance level of 0.05? So this is the significance level. Remember, for something to be statistically significant, our p-value has to be smaller than this significance level. And it looks like only our sample is 3.15 that were statistically significant. All right, so right. So we're going to reject the null hypothesis. Okay, remember the null hypothesis was that the mean was 2.8. Okay, and then we'll go report the alternative hypothesis. Part H. What if we change the significance level to be 0.01? Okay, it has to be less than that, and none of our p-values are. So neither of the samples have enough evidence to be statistically significant if alpha is equal to 0.01. Okay, so this is a rough example, not a rough example, but a pretty easy example of what you'll do for chapter 9.